quantum number. The magnetic quantum number. Very, very important. Magnetic what? Quantum number. The magnetic quantum number. The magnetic quantum what number? Facts you need to know concerning the magnetic quantum number. We shall be looking at them one after the other. Please open your mind so that you can have a well-word, comprehensive knowledge of it, as it will influence your performance in competitive examination. Number one, the magnetic quantum number. The magnetic quantum number conventionally is designated as m sub of the azimuthal quantum number, that is m what L. This is a symbol used in what designating or representing the magnetic quantum what number. Point number two, this particular quantum number was first discovered by Peter Zeeman in the year 1896. He discovered from his experiment that when a strong electromagnetic field is applied to a source that is emitting spectral lines, each of the spectral line gets split into a number of lines. This phenomenon is today known as the Zeeman effect. In order to provide an explanation for his observation, Zeeman asserted that what the electron that is producing these lines has indeed a magnetic field with several possible orientation for the same number of azimuthal quantum number. This was eventually authenticated by Landau. That is point number two. Point number three, the magnetic quantum number. Take note of that. I said point number one, magnetic quantum number is designated as ML. Point number two, it was discovered by Peter Zeeman in 1896 from his experiment, which is today known as the Zeeman effect. Then point number three, the magnetic quantum number particularly was invented to determine the direction of orientation of the electrons in the atomic orbiter. The direction of orientation of the atomic orbiter in space can be obtained with the knowledge of the magnetic quantum number. I think there is a formula for it that says that L is equals to I think there is a formula for calculating Lz is equals to H. Okay, the formula says that L is equals to H all over 2 pi and close the bracket M L. Here ML is the magnetic quantum number. H is known as Planck constant, and of course this is 2 pi, and Lz could be used to determine the direction of orientation. Could be used to determine rather what the value of L is known, the direction of orientation of the atomic orbiter in space could be obtained. That is one key or primary function of the magnetic quantum number. It determines the direction of orientation of the atomic orbiter, whether in the x-axis, y-axis, or the z-axis. Number 4 information you need to know concerning the magnetic quantum number. The magnetic quantum number. The magnetic quantum number divides each of the subshells into sub-subshells. Take note, please, that there is the azimuthal quantum number, which has been extensively discussed. And I told you in the course of that lecture that the azimuthal quantum number divides the shell, KLNN, and so on, into subshell. Now we're not talking about the division of this subshell, SPDF, subshell, which originated from the principal shells, KLMN, OP, and so on. What quantum number divides this subshell into subshell? It is the magnetic quantum number. Subshells are further divided into subshells as a result of the magnetic quantum number. How does it do it? Number of subshells, that is magnetic quantum number, is equal to 2 L plus 1. With this formula, we can compute the number of such shares that are contained in a given what subshare. Sorry, the number of subshares that are contained in a given what subshare. Let's do that. For instance, when the principal quantum number is 1, we obtain the azimuthal quantum number to be n minus 1, and that is equals to 1 minus 1, and that is equal to 0. And this corresponds with what is called the S subshare. Inside of the S subshare, there are other what share, else we call them subshare. How do we get it? We can do that or justify that using the knowledge of the magnetic quantum number, which by formula says Ml is equivalent to 2n plus what? 1. So in this case, when n is equal to 1, L has been established to be 1, and that corresponds with the what? The S subshare. So by formula we have n what? L to be equal to 2 into bracket 0 plus what? 1, and that is equal to 0 plus 1, and that will produce what? 1. Meaning that what? There is only one subshare. We have only S what? Sub what share, which originated from the principal share known as what? The K share. And that when n is equals to what? 2. We have n to be equals to 2 minus 1, and that is equals to what? 1, which corresponds with the subshare known as the P what? Subshare. The question is, how many subshare do you have in the picture? We can do that by saying Nn is equals to 2n plus what? 1, and that is equals to 2 into bracket 1 plus 1, and that will produce what? 3. Meaning that inside of what? The P subshare, there are 3 subshares. Meaning that we have 3 types of what? P atomic what? Orbital, which is today designated as the PS, the Py, and the what? The Pz. These are the 3 subshares that are contained inside of the P sub what share. So take note. Under examination condition, you may be what? Evaluated based on that. That how many subshares do we have in a subshare known as what? P. And the problem will ask you for a principal quantum number of 2, which is a principal share. Of course, it is what? L. Now, how many subshares do we have in L? Of course, we have 2, which is S and P. The next question is, how many what subshares do you have in the P? How many subshares do you have in the P what subshare? You can do that using the formula, which of course, in the end thereof, will result to 3 subshares, meaning that there are 3 types of what? P atomic what? Orbital, and they are conventionally today designated as PS, Py, and of course Pz. The next is, when what? The azimuthal quantum number n is equal to what? 3. It's going to give us L to be equal to n. I mean, when the principal quantum number is equal to 3, azimuthal quantum number becomes n minus 1, and that's 3 minus what? 1. And that will produce what? 2, which corresponds with the D subshare. The D what? Subshare. The question is, how many subshares do we have inside of the D what? Subshare? It is Ml is equals to what? 2n plus what? 1, and that is equals to 2 into bracket 2 plus what? 1, and that will give us 5. Meaning that inside of what? The D sub what shares, there are what? Additional what? 5 subshares. In other words, the D atomic orbital is divided into 5 types, which are today called the D SY, the D SZ, the D YZ, the D S square Y square, and of course the DZ square. These are the 5 types. Please have this at the back of your mind. It's going to enhance your performance professionally in writing the electronic configuration of the various what elements as we have them documented in the iconic version of the periodic table. So how many subshares do we have in the D1 subshare? There are 5 in number, and they are being designated as DXY, DSZ, DYZ, DS square Y square, and of course DZ what square. Now what about when the principal quantum number is what? 4? Of course, we have azimuthal quantum number as n minus 1, and that's equal to 3, 4 minus 1, and that will give us 3. And this corresponds with what? The F what sub what share. The question is, how many subshares do you have in the what? The fundamental what? Orbital, otherwise known as the F what? Sub shell. It is what? NL equal 2L plus 1, and that is equal to 2 into bracket 3 plus 1, and that will produce what is called 7 of 8. Meaning that there are 7 types of what? The F atomic what? Orbital. In other words, you have 7 sub shells contained in the F sub what? Shell. And these are today conventionally designated as F of S into bracket S squared minus Y squared, F of Y into bracket S squared minus Y squared, F of Z into bracket S squared minus Y squared. Then you have F of S, Y, Z. You have F of, okay, you have 1, 2, 3, 4, 5. Then you have F of Z what? Q. Then you have F of X, Z squared, and you have F of Y, S, Y what? S what squared. So these are the 7 times of what? Sub-shells that are contained in the F what? Sub-shells. Like I said before, please, all efforts must be made to what? Have a master knowledge of each of the sub-shells, because it will enhance your writing of the electronic configuration of any given element as contained in the periodic table more professionally. So take note of that. Inside of what? The S1 subshell, there is only one subshell. Inside of what? The P subshell, there are what? 3 subshell, known as what? The PS, the PY, and of course the PZ. Inside of the D subshell, there are 5 subshells, known as the DSY subshell, DSZ, DYZ, DSY square, and of course the DZ square. And finally, for now, inside of the F subshell, there are 7 subshells, known as F of X, S square minus Y square, Fy S square minus Y square, Fz S square minus Y square, Fxyz Fz cube, Fsz square, and of course Fy square. These are the 7 subshells that are contained inside of what? The SP, that are contained inside of what? The F subshell. Most importantly, take note of it, that what? The magnetic quantum number divides the subshell into subshells. Like I said before, don't confuse this with the azimuthal quantum number. What the azimuthal quantum number does is that it divides the principal shells into subshells, whereas the magnetic quantum number further divides the subshells into subshells. And this we can validate mathematically using a formula that says that ML, which is magnetic quantum number, is equal to 2L plus what? 1, where L is known as the azimuthal quantum what? Number. Another significant fact that you need to know concerning the magnetic quantum number is that what? The magnetic quantum number can only take possible values ranging from minus L to what? Plus what? L. Meaning that once you have a knowledge of what the azimuthal quantum number, you can as well what? Write completely and correctly the various possible numbers that what the magnetic quantum number can what? Accommodate. How do we do that? For instance, when N is equal to what? 1, azimuthal quantum number is N minus 1, and that is equal to 1 minus 1, and that is equal to what? 0. Take note of that. Take note of that. Now, when N is equal to what? 2, yes, azimuthal quantum number is equal to N minus 1, and that is equal to what? 2 minus 1, and that is equal to what? 1. When N is equal to, now, when N is equal to 2, azimuthal quantum number is N minus 1 is equal to 2 minus 1, and that is equal to what? 0. Therefore, possible what values ranges from minus N to what? Plus N. Meaning that N is 1, so we have minus what? 1. Then before you get to plus 1, you have to go through what? 0. Then after you have plus what? 1. For a principal quantum number of 2, the azimuthal quantum number is 1. The azimuthal quantum number is what? 1. Whereas the magnetic quantum what number ranges from -1 to plus what? 1. That is -1, 0, and of course plus 1. Meaning that they will quiz you or what evaluate you under examination condition to write the possible what? Values of the magnetic quantum number for a principal quantum number of 3. What do? We do it. That when n is equal to what? 3, n is equal to what? n minus 1. Therefore, n is equal to what? 3 minus 1, and that's equal to 2. Finally, azimuthal quantum number can take value ranging from where? -n to what? Plus what? n. So what is the azimuthal quantum number obtained or calculated? It is 2. Therefore, the possible values of the magnetic quantum number for a principal quantum number of 3 ranging from -2, -1, 0, 1, and of course plus what? 2. For what? A principal quantum number of what? 4. I think the azimuthal quantum number will be what? 3. Therefore, the magnetic quantum number which ranges from -n to what? Plus n, the values becomes -3, -2, -1, 0, 1, 2, 3. So these are the possible values of the magnetic quantum number for a principal quantum number of what? 3. So you can see with the help of what? The knowledge of the magnetic quantum number, we can also bring out the various what? Quantum what? Numbers, values that each of the electrons in a given atomic orbital is meant to what? Have. For instance, now, let me establish what this. Look at it. Let's look at this. Now, for a principal quantum number of what? 2, I think we are going to have azimuthal quantum number of what? n minus 1, and that is equal to what? 1. Of course, then the possible values of what? Remember that for a principal quantum of 2, azimuthal quantum of 1, we are talking about what? The P what? Subshell. We are talking about the what? The P what? Subshell. Then inside of this P subshell, we have Nl to be equal to 2 what? L plus what? 1, and that is going to produce what? 3. Meaning that we have 3 of what? P subshells, which are Ps, of course, Py and what? Pz. The question now is, what are the quantum numbers that each of these what? Subshells are characterized or what? Are designated what with? It is with the knowledge of the possible values of what? The magnetic quantum number that we can establish that by saying that what the possible values range from what? -n to what? Plus n. To what? Plus what? n. When what? Azimuthal quantum number is what? 1. The possible value becomes what? -1, 0, and what? 1. Then that what? For what? Ps, the azimuthal quantum number is what? For Ps, rather, the magnetic quantum number is what? 1. For P what? Y, the magnetic quantum number is what? 0. And of course, for P what? Z, the magnetic quantum number is 1. So this is how you can what? Assign possible what? Quantum what? Numbers to what? Each of the subshells as contained in what? Each of what? The sub shell. Another very important what? Knowledge concerning the magnetic what? Quantum what? Number. So I think with this, we have been able to establish conclusively all you need to know concerning the magnetic quantum number, especially on the aspect of dividing the subshell into sub-shell. Please have that at the back of your mind. And most significantly, don't forget it. And I ask you, it is a conventional question, yes? Which of the world quantum numbers determine the direction of orientation of the atomic orbital in space? It is principally the GP of the magnetic quantum number. With this, I think I've been able to come to the conclusion of all you need to know concerning the magnetic quantum number. The last on the list is known as the spin quantum number. There is no way we can be applauded to have what? Treated completely quantum numbers without giving due intelligence to this most important aspect of the quantum numbers, known as the spin quantum numbers. The spin quantum number. To do this, there are principles we need to what? Have and injected and directed knowledge of. One of such principles is called the Pauline exclusion principle. The Pauline exclusion principle. What is this principle all about?